Hello everyone, and welcome to this special edition of QWave, the webinar series of the European Quantum Industry Consortium, QuIC, our acronym. My name is Thierry, I'm the Executive Director of QuIC, and I'm delighted to welcome you today for World Quantum Day, April 14th. Why is today World Quantum Day? Stay with us to find out. And I'm thrilled today to be accompanied by three fantastic panelists to take us through what we're celebrating, how this inscribes itself in the International Year of Quantum this year, 2025, and what we can expect from quantum technologies in the year to come. My three speakers, first, Professor Elham Kashefi, decorated professor in both France and the UK, member of the National Quantum Computing Center, and co-founder of VeriQloud. Welcome, Elham.
Thanks for having me.
Professor Tommaso Calarco, from the University of Bologna and co-founder of the company Cruise. Welcome, Tommaso.
Hi, everyone.
And Olivier Ezratty, author, academic, and co-founder of the Quantum Energy Initiative. Welcome, Olivier.
Hello, everybody.
So today is April 14th. Why are we celebrating World Quantum Day on April 14th? To find out, you have to stick with us till the end. We'll give you the clues at the end. For now, I'd like to start with all three of you to take a look back, a step back. And Tommaso, I'll begin with you. This year, 2025, is the International Year of Quantum Science and Technology. Why 2025? What key discoveries, moments from the past are really marking this year as a year to celebrate?
Well, this is a year in which, three very important papers as the foundation of quantum mechanics have been published. It was a year of, let's say, high density of quantum development. But really, when we were discussing together with a big panel of, big network of experts and also historians, where to put the origin, we decided against the, let's say, usual, and this is again a hint, but we will disclose it at the end, as you said, against the usual birthday of a male old white quantum scientist, but rather to celebrate really discovery. And it was not straightforward, it was not entirely obvious. And so we converged because of these three important papers, which were published in that year from Heisenberg, from Schrödinger and colleagues. And this is sort of a nice metaphor also for what we have nowadays in terms of a collective effort. So it's not one individual person, not one individual institution, not one individual country. It's more like a race, like quantum technologies, between humankind and nature to understand and master it. So we are celebrating all of that now.
Yeah. So scientists coming together 100 years ago, Schrödinger, others, to wrestle with what the science meant. Olivier, we look over time, 100 years of discoveries. For you, what are some of the most major scientific milestones in quantum as you look back to that history?
There are so many, it's very hard. I'll pick the usual one, which is the Bell inequalities violation by Alain Aspect in 1982. Why? It was based on the work from John Stewart-Bell in 1964. And I mean, it was the beginning of the so-called second quantum revolution, because everything we do right now is based on that. Whether QKD, quantum key distribution, quantum computing, even quantum sensing is based on that, kind of discovery. But I had another one, which came later, which is on the other side of things, of physics. It's algorithms. Quantum algorithms, they were created about 30 years ago. There's the role of people who are known and other lesser known. For example, David Coppersmith, the guy who invented the quantum Fourier transform. Then Peter Shor for integer factoring and D-log. And then Alexei Kitaev in 95, I think, is probably not well enough known for his role in inventing the so-called QPE, which is the basis of quantum chemistry. So I would like to give credit to all these guys. And I will add another one, which, because we talk about team playing, it's another unknown, a guy named Benjamin Schumacher. It's not a race car driver, and he created the word qubit in 95. So he had some legacy to some extent.
So from early scientific discoveries to writing qubit in '95, that's quite the travails. That's quite the history. Elham, over this period of time, there was a lot of deep questions that were being asked, and as answers were coming up, there was a sense that there might actually be not just science to be done, but potential applications to this. For you, when do you think that we started as a collective, as humans, to sort of transition from science to possible commercial application for quantum?
That's a great question. I will answer it in two parts because I think different community start realizing this commercial potential in a different way. And is essentially following up what Tommaso and Olivier was mentioning. For those of us coming from theoretical computer science and quantum information, we actually saw the commercial potential quite early, as Olivier was mentioning. In fact, what's fascinating is that many of the features that physicists historically thought of, the bug, superposition, no cloning, entanglement, all these phenomena, we start reinterpreting them as a powerful resources. If you look at that shift already happened in late 80s and 90s, think of BB84, Eckert entanglement based protocol, shows algorithm for factoring, Grover stage, the usual suspect. For me, why I'm repeating them, because they were not just some isolated trick, they actually opened a whole new design space for information processing. And already by 2000, 2010, especially within the QuIC community, we already had a growing list of provable quantum advantage, which will start begging for this commercialization, unforgeable quantum money, verifiable delegated computing, secure random generation, exponential communication complexity. The list can go on and on and on. So my argument is that ICT community essentially had written the catalog of quantum application long before hardware starts supporting them. But of course, the hardware perspective, the other part, the realization came much later, and understandably so. The devices simply weren't there. It wasn't until the mid to late 2010, with the rise of superconducting qubit ion trap photonic chip, that engineer and experimental physicists started to see that, okay, some of these theoretical protocol might be actually feasible. And that's when serious momentum, national program like UK National Quantum Technology, EU flagship, US NQA Act, they all come to help this bridge between theory and the commercialization that you're asking. So for me, different community come with a different timeline, but now, as Tommaso was mentioning, they all come together now.
And when you put this all together, you create this catalog. Would you say that people very early on realize, goodness, this is not just one technology, one area, it's an entire array that can be impacted by this technology?
100%. I mean, I will come back and say that, during long time ago, we were considering ourselves as like a science fiction, and not the community of computer science or ICT were taking it seriously. But I think it is like you were given a new toolbox, like the kids, and they're given something completely novel. And whenever you give to scientists a different perspective, a different tool, you suddenly go with all the challenges. So I think the excitement from very, very early on, from my very first QIP that I attended, it was the fact that we are here to use a complete novel way of thinking about information processing, addressing all the challenges that we all are aware of it, from computational to security to accuracy, etc. So I would claim that definitely from application, algorithm, protocol design, theory side, we were excited that we are rewriting the history and we have the tools. We just needed to wait for somebody to build those tools, but we were using them already.
So as we look in this impressive history, going all the way back to Schrödinger, maybe one name that is not so familiar is Richard Feynman, an American physicist who was famous for quoting that in order to really understand quantum physics, you need a quantum computer, which was seemingly a self-fulfilling statement, but a really provocative one back in the early 1980s when it was made. And we have to go back to that time. Computers themselves, standard computers as we know them today, were just coming to life. So Olivier, if I have to challenge you in putting one marker in time where quantum computers as we know them today coming online really kicked off, would you agree that the early 1980s was it?
Yes, but I wouldn't credit only Richard Feynman. I would like to credit two other guys who had ideas even before Feynman. I mean, there was Yuri Malin, a scientist from the USSR back then, and Paul Benioff, who before Feynman had the idea to create a quantum computer based on so-called gate-based model, the one we use in majority right now. And then Feynman talked about mostly the idea of a quantum simulator using what we would name today an analog quantum simulator. But then there was a lot of work, not just Richard Feynman. I mean, most of the theory was created by David Deutsch between 82 and 85. So all that led to all the quantum information science that Elham was talking about. And it took a lot of years to develop algorithms, so about more than 10 years, starting in 92 with David Deutsch and Richard Josa. And then we had the first commercial system with, I think, D-Wave in 2012, and then IBM in 2016. So it's a long story, I mean, for about 45 years now.
And for you, Elham, any other events, markers that really show this transition out of the lab to applications from those initial ideas to really concrete hardware that people could work with?
I agree with Olivier that it's very hard to put marker, because the amazing thing about our field is that it's really a continuous analog evolution, if you wish, and that's remarkable. You know, we're talking about 100 years of celebration, and we're seeing year after year, researcher by researcher, scientist by scientist, everybody bringing one part of the puzzle. And I'll come back to this point of how this is the strength of our field. But if you really want me to highlight a few things, maybe I'll bring some other element just to complement what Olivier was saying. In 90s and 2000, a crucial turning point was that we started seeing setting up beyond pure academic research, and you could see the very first sign of industrial ecosystem already forming back 25 years ago. Especially, interestingly enough, sometimes people don't appreciate it. We're talking a lot about quantum computing, but in quantum communication, that industry ecosystem started way earlier. One of the clearest indication for me was the quantum key distribution. In early 2000, company like ID Quantic, Magic Q Technology were already building these devices and selling these devices around the same lab, Toshiba, Cambridge, Los Alamos, and NEC. So these experiments at the level of metropolitan fiber network, they are incredible, because they are not just proof of concept, they are actually a demonstration. Even very importantly, standardization came into the picture. The work that ETSI at industry specification was trying to do. These are all the shift, we're talking about the industry getting import. So they were all being formalized and prepared for real world integration, if you want this as infrastructure. And that's exactly the space I work in. That's why I'm very fascinated. It's what we do in VeriQloud, making this application viable based on the infrastructure that has been built since 2000 already, and your QCI, which we might hear about it again more on it. So that's really on quantum communication side, and we can go on the quantum sensing and quantum imaging, etc. But just to make this short, back to the quantum computing, and as Olivier mentioned, I think D-Wave, which was founded in 1990, was also a turning point. It's created a lot of public attention, although sometimes controversial in terms of scientific claim, but it did mark a shift. It was suddenly we have a venture capital, a private lab, company hiring quantum engineer. These are also another point of this market. Around the same time, big player like IBM, Microsoft, forming internal quantum team. You had places like Station Q that was explicitly industry academic collaboration. So the theoretical groundwork had been laid earlier, as we discussed, but I guess in 2000, we started to see this actual hardware field trial, organizational investment that started saying the beginning of that transition from science to industrial momentum.
So science is pushing forward, bringing industry or this technology out of the lab and into commercial applications. It's a global one. D-Wave from Canada, many of the efforts here in Europe, scientific ones in the US, IBM, for instance, was mentioned. Through this history, a lot of the science was focused on bringing tech to the real world. Tommaso, to you. now that we have this tech, and as it was coming out of the lab, were there feedback to the science itself? Was science also evolving based on the fact that this technology was starting to really be commercial?
Well, for sure. And I will give a couple examples from the second quantum revolution. But I mean, the biggest example from the first quantum revolution is in everyone's hands and pockets. Because the first quantum revolution is what brought us the transistor, what brought us actually accessible digital computers. And I do not think that I have to convince anybody about the impact of that. It would be entirely impossible. The whole field of numerical analysis, simulation, artificial intelligence, what have you, which of course has impacted and supported a lot also scientific research and a lot of development in many fields of science, I mean, would be completely unthinkable without the first quantum revolution. But then if we think about the second quantum revolution, well, we move forward more, for instance, about like enabling technologies like highly specialized, highly stable lasers, for instance. This is still first quantum revolution, but this is part of the toolbox which is necessary to make those, for instance, atomic quantum computers based on optical tweezers and so on. So, I mean, this kind of thing is something where we have seen companies, specialized companies, developing new laser systems, for instance, which have enormously accelerated the pace of scientific discovery because they enable things which simply were unthinkable before. And now if you go really to devices of the second quantum revolution, if we think of single photon sources and single photon detectors, they have been originally developed, of course, for quantum communication applications, as Elham was mentioning, because this is what we need to enable the first protocols like BB84 for quantum cryptography, quantum key distribution, and so on. But as a matter of fact, these have led to a host of new possibilities within research in terms of the opening even new fields in terms of quantum imaging, for instance, which can be based on single photons, sources and the detectors. And a lot of this is really something which sort of is just coming from the back and forth, because not only is it a collective effort, but also it is an effort in which, really science and industry are very deeply intertwined. To come back to the first answer that Olivier was giving, rightfully crediting the Bell inequalities and the experiment by Alain Aspect with, being an important milestone, maybe a central milestone, maybe the main milestone in the history of quantum technologies of the second quantum revolution. As a matter of fact, the very same Clauser-Horner-Shimoni-Holt inequality, which is used to show whether reality exists locally or not, is the same thing which is used to certify in a device-independent way whether a quantum repeater is secure. And this is, for me, a fantastic example of something which is totally philosophical. And when Alain was starting his career, was so useless that people were promising you will ruin your career. And the only reason why we are sitting here today having this conversation is because with 31 years of age, he had a full permanent position in the French system, so he could not care about how he would ruin his career according to other colleagues, and that's why we are here. So this completely philosophical, useless, crackpot stuff, and using it directly for authentication of quantum devices. This is something which I still consider extremely fascinating and really shows this constant back and forth, and we could say osmosis between research and industry in both directions indeed.
And for listeners who are maybe surprised by some of this scientific jargon, just note that BB84, other protocols are all stemming from these fundamental quantum properties: superposition, the opportunity for quantum systems to be in two states at the same time, and entanglement. No need to know the exact physics behind it, but just knowing that those two characteristics, when put together in different combination, can give you protocols for communication, like BB84, and also protocols for quantum computing, some of these algorithms that were listed beforehand. So wow, we put this all together. We come to today, 2025. We're celebrating the International Year of Quantum Science and Technology. And as we're doing that, we're looking at where we stand today, the tools we have today, those new technologies, the many companies that we have today that are specializing in one or the other areas of quantum. So Elham, first to you. What excites you the most about today? I mean, there's so much that's already happened. What do we have to look forward to?
Wow. Now you're asking the question. So I can tell you. So what excites me the most is that we are finally entering a phase where everything is really starting to come together. Although this is not just a sentence, we already say that how the field comes from so many different backgrounds. We heard about physicists, mathematicians, experimentalists, and they all build a pillar. But then we all went and explored those pillars. But now we're coming back again. It's just like, it's another big bang is happening in here. We really bring in theory, hardware, protocol, application. We have moved beyond isolated proof of concept, as I was mentioning. In fact, the entire quantum stack is now under active development and critically under coordination. That's very, very important, which is bringing the role of the QuICs into the picture. And I have the chance to the reason I'm overexcited about this question, because I've been part of this coordination, if you want, the chance experiencing it from multiple angles, whether I do academic research in Edinburgh and CNRS or doing, launching quantum software lab and VeriQloud as an industry or at the national level at the NQCC, we are already seeing that they are all the same. When people are saying why we are doing all of these things, because they are the same. These are all this setting. They have one thing driving all of us from different angles. We are not just building quantum tech, but we are demonstrating provable quantum advantage with impact. And I stand by this sentence. This is no longer a vague promises. It's by the result that we can verify. We talk about certification, Tommaso was mentioning. We can verify, benchmark, and build up the trust. And that's, for me, a turning point. The mission is no longer to be speculative and do funky statement in the party, but we are really talking about actionable mission for us. What I think is still under discussed and sometimes misunderstood is the nature of this challenge. Okay, I want to take this opportunity to say, and this is not like a moonshot with a single launch date. Okay, it's not a single company race. This is a massive integration effort. It's about aligning the entire community, physicists, engineers, theorists, computer scientists, industry, government. They all come together to co-design systems that are not just powerful but reliable and transparent. I want to push, we're talking to the public. Too often public narrative focus on quantum supremacy or just the qubit count. But we have gone beyond that. Now this is the year that we are now, we are investing in verification and certification in the tool that make quantum technology trustworthy and what turns prototype into the infrastructure. So for me, 2025 isn't just a celebration of the progress, is in fact is a call for deepening up our collaboration to reconnect all this layer of the stack and to remember that no single nation or company or lab will deliver this alone.
The challenge is there. The challenge is set. Tommaso, in your view, is there aspects of this emergence of quantum technologies that is perhaps under-discussed, overlooked, and that we should have at the forefront of our minds as we look ahead to how this sector is going to develop?
Well, there are many, of course. The first one is that quantum technology is, as we have discussed here, but this is not so present in the sort of public awareness, is not just quantum computing. It's a range of technologies which encompasses also quantum, not only quantum simulation, which can be regarded as a branch of quantum computing, as you mentioned before, but also quantum communication, sensing, and metrology. So this is one aspect which, is not so present to the public, and actually, the most commercially mature aspects and branches of quantum technologies are from communication and sensing, and they can bring significant advantages which are not like the AI which some people expect the day after tomorrow from quantum. So another aspect which is overlooked is care about hype. Here at Forschungszentrum Munich, I'm the director of the Institute of Quantum Control, but what I do a lot of my time is quantum hype control, in the sense that, especially from industry, I should say, sometimes, of course, if you are a startup, you have to sell your things, so of course you will change the world tomorrow, and if you are in a big corporation, you have to convince your CEO that, of course, they should shower you with cash, but even though this may be understandable, we as scientists, we have a role in kind of making clear what can be the promise. And actually, we have been, as Elham said, we have been and we keep being surprised by how much reality overcomes what we expect. But still, is not around the corner. Still, it's a challenge. Still, it's long-term. Still, it's very much a research problem. So the aspect of distinguishing hype from reality is something which should be much more present in the public discussion, in my opinion. And something which also is emerging now, and I'm very excited about this, is sort of a broader understanding of the need for discussing ethical aspects and societal implications in a way which is different from what we see, for instance, in AI, which was developed, and oops, and now what do we do? And one can say, so one attitude is, which some colleagues in general, I'm not speaking of any specific colleagues, but some scientists may have the attitude, oh, we just develop tools, it is great, and then society will have to decide what to do. Like, first we develop, and then here's the tool, please decide. But that's not really accurate, because all things are intertwined. For instance, a trivial example concerning AI, while you develop AI, you can do this by taking into account how much is the power consumption that you need to develop your large language model, for instance, or you could ignore that. And depending on this, you get maybe different results. But in the end, if you have thought about the problem that you have about climate impact, you may have a better performing LLM, large language model, which still is not sucking 20% of your electricity consumption like in Ireland nowadays. So asking this question while you develop can help getting to better solutions. And some colleagues may think, oh no, what do all these people want? They know nothing about quantum. Why should they tell us how we conduct our own research? And my answer is, that's exactly the point. Precisely because they don't know anything about quantum research, that's where society should have a say. Of course, they cannot tell us, you choose this problem or this other problem, you solve this in a way. But they should society should be engaged in pointing the scientific and industry community towards what are some sort of boundary conditions, some sort of preferred avenues, how to guide, also to contribute guiding, our common undertaking. Because this is not just science and industry, it's science, industry, policymaking, society, everybody engaged.
That's a really powerful remark, Tommaso. Olivier, you were part of the birth of the Quantum Energy Initiative. The public, so those who are experts and the non-experts equally so, are part of this effort and must work together to bring it forward?
Yeah, sure. I mean, the goal of this initiative was to look at the energetics of all quantum technologies, probably mostly on computing and communication, because sensing is not a potentially broadly used technology. And there were two things in mind. One is there was some thought that there would be some kind of quantum energy advantage with those technology, particularly computing, but we are not really sure about it. And the other one, which makes a lot of sense, particularly for large-scale systems, is how do you make sure that the energy consumption of the system is reasonable and acceptable, particularly when they are very large systems. When you look at the resource estimates for very large thousand logical qubit quantum computers from the future, it may become very large systems. And what we discovered is the power range of the systems is from 1 to 100. So there's going to be a kind of Darwinism in that space. Some companies will have to figure out a way to be energetically friendly. But this is a mix of scientific endeavor and engineering challenges, which is, by the way, at the image of that field. What amazes me a lot in the quantum computing world is that we are working on the science and engineering in parallel. Not serialized in a serialized way like we've done in the past for many new IT revolutions. The other example, which is connected to what Elham was saying, is that we are working on software and even software engineering in parallel with building the hardware. When usually we have the hardware and then we build the software. So this parallelization of the problems is amazing, and it's up to a point where we may also discover some some limitations of our understanding of science itself. So, for example, all companies are trying to build a system with zillions of physical qubits to manage quantum computing, and we don't know what's going to be the limits of entanglement at scale. So, at some point, we may reach the limits of theory, maybe build some new theory, or understand noise at scale, and it's amazing because it's not just about some Moore's law that happened in the classical world. It's about looking at the limits of science. And I'm very excited by that, by the way, because it's exciting to see that we are reaching the limits of engineering and science all together, and people are working on that and in some coordinated way, preferably. So that's what excites me in this world.
This is a fantastic segue to the last part of our conversation today. A lot of people have listened to us over the past minutes. They might not have understood some of these acronyms, might not be very familiar with quantum computers, quantum computing, quantum communication. What will it mean for me? How will it impact my life, our lives? So question to each of you, and I'll start with you, Olivier. What should people keep in mind that can give them some confidence and certainly optimism as these quantum systems not only spring out of the labs as they already have, but really start to enter day-to-day lives?
Well, I would like to start with a joke. First, quantum scientists, they don't kill any cats. That's because everybody thinks about quantum physics as a kind of cat that's dead and alive. So that's one thing. The other thing is, you have serious and passionate people in this world, very young for many of them, all the PhDs and postdocs, they are very young people. So it's this kind of, when I see the startups, when I see the academic teams, I see a young generation creating the tools for the future. That's what excites me a lot. I see a lot of imagination because, for example, when you look at the problems we are facing, how do you scale quantum computer? How do you make quantum sensors that work at scale as well, miniaturized? How do you manage secured quantum communication also at scale? When you see all those challenges, some of them looks kind of unbearable. It's very difficult, but I'm betting on the imagination from all these young people, and older, of course, but and betting on the human creativity is the main asset of that world. And I'm always surprised by the new stuff that's coming out of the academic world and the industry about so new ways to fix problems like quantum error correction in the case of quantum computing, finding new algorithms which are circumventing the problems with scale and other things like this. So trust the scientists, and we are in a world where we need to trust scientists more than what we do right now politically. So trust the scientists, trust the engineers, trust the way those people work together, because you need to have a lot of collaboration between all these stakeholders to make things happen.
Fantastic. That's a great, encouraging word. So from each of you, one sentence, what are you most looking forward to in the years to come? Tommaso, I'll start with you.
I'm looking forward for the advantage of quantum technologies, each one of them, to be shared globally, not to be in the hands of a few, but to really bring to benefit for the whole of the global society. This seems to be very much in the opposite tendency to what we witness today. So let's hope that quantum science will keep doing what science does, building bridges.
Lovely. Olivier.
Wow. Yeah. It's a big part of my specialization, so I would love to see in my lifetime scalable quantum computing solving the problems I've been advocating for a while. Solving quantum chemistry problems, optimization problems, even to some extent machine learning problems. So there are many, many things where quantum computing can help science mostly, not just businesses, but help science move forward.
Thanks, Olivier. Elham.
Oh, one sentence. That's going to be a long quantum sentence. Okay, for me, I would say quantum offers a unique chance to rebuild trust in digital infrastructure with secure, verifiable, and fundamentally transparent technology. And as we discussed, also for me, we need to think about quantum as completely new tools. And it's also really the next step of civilization. So I don't know what other people are doing. They should all join to this quantum race.
Fantastic stuff. Fantastic stuff. We started this session today together by saying that April 14th was World Quantum Day. Why is that? So for those of you who guessed Planck and the Planck constant, congratulations. Indeed, 414 in electron volts seconds, Planck's constant, 4.14, is the reason why today, April 14th, we come together to celebrate quantum science and quantum technologies. Tommaso, Olivier, Elham, thank you, all three of you, for being with us today. Before we go, to each of you the chance to wish everyone a happy World Quantum Day. Tommaso.
Buona giornata quantistica a tutti.
Olivier.
Bonne année quantique.
And Elham.
Well, buongiorno quantique, Ruza Quantum Mubarak, happy Quantum Day.
Thank you, all three of you, for being with us today. Thank you for being part of this special edition of QWave. For those of you wanting to find out more about the quantum world and quantum industry, check out QExpo. It's Europe's largest quantum industry event happening May 14th and 15th in Amsterdam. Open doors, free to all, a great opportunity to see what's happening. To find out more about our organization, the European Quantum Industry Consortium, QuIC is our acronym, follow us online on LinkedIn, as well as our website, euroquic.org. We look forward to seeing you next time. Thanks for joining.